So far we spoke about two types of collisions. We spoke about elastic collisions as well as inelastic collisions. But what we've really spoken about is what happens to our objects before the collision and after collision. So we said that in elastic collisions, both kinetic energy and momentum are conserved. And we said that for inelastic collisions, only momentum is conserved. Now in this lecture, we're going to focus primarily on what happens to our objects as they actually make contact. So what happens during the actual collision when the two objects are in contact? So suppose at time equals 0 seconds, our two objects begin traveling. So this is object number 1, my soccer ball, and object number 2, my hand. And suppose the two objects begin traveling towards one another, and time equals initial, or time equals 0, is the point at which the two objects touch. And time equals final is the point at which the two objects separate and begin moving in opposite directions. So what happens when the two objects actually touch? Well, we said these two objects actually deform according to Hooke's law, which is a conservative force. Now, what happens to our force right before our collision? So what happens from the time equals 0 seconds to the time initial? So the force is 0, and that's because my two objects are not yet touching. There's no physical force acting on my two objects, and that means the force must be 0. Now, when the two objects actually touch, that's when they begin feeling a force. This object exerts a force on my hand, and my hand exerts a force on the object according to Hooke's law. Now, initially the force is very small, and somewhere in between the force gets bigger and bigger, and then the force begins getting smaller, and the two objects move apart. So let's plot this on the y-x-axis, where the y-axis is my force in newtons, and x is my time in seconds. So at time equals 0, up to my initial time when my two objects make contact, my force is 0. And that's once again because my two objects are not physically touching. So there is no physical force that my two objects feels. Now, as soon as my two objects begin touching, they begin feeling a force. So if you choose any time on this axis, you will see that there is in fact a force. And to find the maximum force, we simply find the time at which the force is at its maximum. Now this curve is simply my function, my force function. In other words, for any t between this interval, I can plug into my function, and that will give me my force, or the magnitude of my force. Now once again, once my objects separate after time final, my force will also be 0, just like my force is 0 in this interval. And that's because my two objects aren't touching. So I want to ask the following question. If I shade this region like I did here, and I find the area of this region, what will that area represent? What is the significance of this area? So this is the question we're going to explore in this lecture. Now, let's begin by remembering what Newton's second law of motion is. According to Newton's second law of motion, an object will accelerate only if it feels a net force. In other words, if there's no net force on my object, that object will not accelerate or decelerate. So F equals ma, where a is my acceleration, m is the mass of the object, and this is my net force acting on my object. So let's rewrite this equation right here. Now, the reason my object 1, my soccer ball, stops moving and then moves in the opposite direction is because there's a force that's acting on that object. Likewise, the reason my hand stops moving in this direction and bounces back this way is because this object exerts a force on my hand according to Hooke's law. So there is a net force acting on my two objects when they're physically touching each other during a collision. And that's what causes my two objects to decelerate and then accelerate in the reverse direction. So force equals ma, where force is my vector and A is my vector. Now let's recall for a second what acceleration is. By definition, acceleration is the change in velocity over change in time. And more specifically, it's an infinitely small change in velocity over an infinitely small change in time. So let's plug that definition into my acceleration, and I get mass multiplied by infinitely small change in velocity divided by an infinitely small change in time. So now let's take this m and plug it inside this guy, and we get an infinitely small change in mass times velocity divided by infinitely small change in time. Now let's recall what m times v is. Well, m times v is simply our momentum. So that means we can replace this m times v with the momentum symbol, so lowercase p. So in fact, we see that the force that the two objects exert on one another, the net force, is simply the infinitely small change in momentum divided by an infinitely small change in time. So force equals change, or the rate of change in momentum. This is simply rate of change. Now, let's do the following. Let's manipulate this equation in the following way. Let's multiply both sides by dt. So let's bring dt on this side, and we get the force, or the net force, multiplied by infinitely small change in time, dt, equals infinitely small change in our momentum. So why is this relevant? Why would we do this? Well, we'll see why in a second. This is very convenient. So now, notice what this is. What happens if we take the integral of this guy? And remember what integration is. Integration basically helps you find the area underneath some curve. So if we have the following curve, f of t, which is basically what this function is here, f of t, we can take the integral of this from t to t naught, or from t naught to t, to help us find the exact area of this curve. And that's exactly what we want to find initially. We want to answer the question of what does the shaded region signify? What's the significance of this blue shaded region underneath this function, this force function? So let's take the integral of both sides. So let's take the integral from t naught, from t initial, to t of the force function d times t equals, now if whatever we do to this side, we have to do to this side. So on this side we're also taking the integral, but because this is d of p and not d of t, we have to use p initial and p final. And notice what happens. This guy we're going to leave as it is, but let's actually solve this integral. Remember, when there's a 1 in front of the infinitely small change in potential, this simply becomes x. So now we're basically taking x, and we want to find what x is from p initial to p final. So we basically take p minus p initial. This is according to the rules of integration. And we see that p final minus p initial is simply the change in p. So that means this whole guy, this area, simply signifies the change in our momentum. Now this is given a special name known as impulse. So the answer to our question, what does the shaded region signify? Well, it signifies our change in potential, which is known as impulse. So impulse is simply change in momentum, and it's given the letter J. And since P is a vector, so is our impulse. So J gets a vector symbol on top. Now, it is sometimes useful to talk about a concept called the average force of a collision, which is basically defined to be a constant force which, if acts over the same time interval, will produce the same exact impulse, will produce the same exact change in potential. So let's see what that means graphically. Suppose I define my average force to be at this point. So this is my average force. Since my average force is constant, that means the curve this guy will produce will be a straight line going along this axis. So what this basically means is if I draw my lines going vertically up from the same time interval, this area, shaded area underneath my curve, will have the same exact magnitude as this blue shaded region. So that means that if I take the integral from this point to this point, I will get the same exact value as this whole integral. In other words, simply finding my change in time and multiplying by my force will give me my area of this figure because it's in fact a rectangle. So this means the following. Force average is multiplied by change in time is the same exact thing as taking the integral from T naught to T final of this thing, of the force of this curve multiplied by dt. So this, which we got down here, is the same exact as the average force multiplied by change in time. And note that this guy is the same thing as change in momentum, so our change in P. So that means this is equivalent to my change in P. So let's write that on top here. So change in P is the same thing as force average multiplied by change in time. So if I want to find what my force average is, I simply take my change in P, change in momentum, and divide that by change in time. And this is an important formula because it gives me what my average force should be